Hi, this is Miss Logan. Today I will be going over collisions with momentum. So as a review, we have our conservation of momentum. And what that tells us is that the total momentum of a system stays constant. Okay. Another way to say this is the total momentum before a collision equals the total momentum after the collision. So regardless of what's going on, it's always going to stay constant. So how does this look as an equation? So we have our momentum before equal to our momentum after, okay? And you can see the abbreviations down here, but we're going to use mostly MVs to describe our momentums. So as a review from our previous flipped lesson, there are two types of collisions. First, our elastic collision is after the collision, the objects separate. In inelastic, they stick together. So the objects are going to have the same exact velocity. And we're going to see that when we look at the actual equations. So let's start out with inelastic collisions. Okay? So before the collision, we have some momentum, which is equal to the momentum after the collision. But let's put in MVs and M1s to make more sense. Okay, so our equation for this, we have M1 and V1, which represents this car. And then we have M2 and V2, so the velocity and mass of the second car. Then they collide, so they actually become one system. So we can actually add the masses together, and we have our velocity. So this is our equation that we are going to use for inelastic collisions. For elastic collision, it's going to look similar, but a little bit different. So we have our initial momentum is equal to our final momentum. Let's put in our M's and V's. So we have M1 and V1 plus M2 and V2. So this is a time when you're doing this equation, you really need to look at the signs. Then we have what's going on after. So we have M1 and V1 final plus M2 and V2 final. So often you are going to solve for the velocity at the end. So that's our equation for elastic collisions. So when we're looking at these types of collisions, there's a couple important things that we need to remember. For both of them, the momentum is conserved, which we just saw through the equation. Kinetic energy is conserved in elastic collisions, and then in inelastic, they stick together. You will also see this through your PhET lab that you are completing over the next few days. Okay, so let's take a moment before we do a word problem to look at what this looks like. So this is an inelastic problem. They're sticking together at the end. Okay, so before we have a momentum of 40 kilogram meters per second. I'm just taking M times V. So that's 4 times 10. And then I have a momentum of 20 kilogram meters per second. So that's just 2 times 10. So my total momentum before, when I add these together, is 60 kilograms meters per second. Afterwards, to check if this is correct, I have a total mass of 20 kilograms and my velocity of 3 meters per second. So if we multiply that out, 20 kg times 3 meters per second, we'll see it also equals 60 kilograms. Now let's do an inelastic word problem. A 1900 kilogram police car going at 12.5 meters per second rear ends a 15 kilogram sedan moving at 3 meters per second. After the collisions, the two cars move together as one. What is their final velocity? So we need to use our inelastic equation. So let's write this out. This is what we're going to use every single time. So let's plug it in. I have my M1 and V1, and then M2 and V2. So let's plug that in. I'm going to combine my masses, so 1950 plus 1500, and then we're solving for VF. So I'm going to write out my work so you can make sure that you're following along and understand how I get my numbers. One of the biggest errors at this point is actually just the algebra. So that's something when you're doing this to really make sure that you're not making mistakes on. Remember, we're solving for VF. So after I solve for VF, I'm going to get 7.28 meters per second. Okay, let's look up an elastic problem. So after a holdup, Caleb flees in his 1575 kilogram getaway car at 20 meters per second. He crashes into a 45 kilogram barrel, which is at rest. If Caleb's car moves at 18.9 meters per second after the collision, how fast does the barrel move after being hit? So let's set this up. We have M1 V1 plus M2 V2. Then we have M1 V1F, so my final, M1 V2F, okay? This is the one we're going to be solving for. So we know our M1 is Caleb's car, and then it's going, and that's our V1. The car, the second car, is our M, and then our V2 is at rest. So that's actually 0. We know that Caleb's car, so MV1F, at the end is moving 18.9 meters per second after the collision, okay? So if we come down to our equation, we don't have to worry about this side. It's at rest. So let's plug in our numbers. So M1, which is 1575, times my velocity equals M1 again, and then the car's new velocity, plus we have our M2 for the second car, and then we have V2F. So as a reminder, this M2 is just for the highway barrel, and that is what we are trying to figure out for our V2F. So let's do the algebra here and make sure that you are following along and doing this with me. As I said in the previous problem, one of the biggest errors is actually just in the algebra part of it. Even though that's something that we are already good at, it's a really common error. Okay, so let's subtract over on this side. So I'm going to get 1732.5 equals 45 VF. And we just divide, and I'm going to get VF equals 38.5 meters per second. So we're going to go through a lot more of these problems in class, so make sure you have your equations down so that we can work on them as a class and you can get better at them and also see different situations.